So we're talking about evaluating the quality of data. That's a huge and important part of science in general and physics in particular. And the main objective is to distinguish between two different ways of looking at the quality of data. One is accuracy, the other is precision. So I'm going to show you a couple of different examples of a visual representation of this idea. And in this case, the dartboard is our space of data collection. So imagine, for instance, we have a scale and we're trying to weigh the mass of something, and let's say we know what the mass should be. Let's say we have a 1 kilogram weight and we're placing it on our scale and measuring what the scale reads out. There's a few different ways that those measurements could be good or bad. One way is they could be close to the bullseye. In this case, that would mean that the scale reads exactly 1 kilogram. Another way that they could be good is that every time I put the weight on the scale, I get exactly the same reading, and there's not a lot of changing or fluctuation. So that first quality of being close to the true value we call accuracy. And that second value of being clustered together so that when you repeat your procedure, you get the same result each time, we call that precision. In this first example, we see that both the precision and the accuracy are quite bad. We can see the accuracy is bad because all of my darts here are far from the bullseye. So most of my measurements are far away from the true value. And I can also see that they're all over the place. They're not consistent. Some are low, some are high. So the precision is really bad as well. Here's an example where we have moderately good accuracy and moderately good precision. Every shot isn't right on the bullseye, but they're all fairly close to the true value, and they're all fairly tightly clustered together. So there is some fluctuation, but it's much more precise than that first example where the darts were just all over the place. Here we have an interesting example where we have lots of precision, but very bad accuracy. You can see that all of my measurements are consistent. Every time I take a measurement, it's landing right in that same region. However, it's not the correct region. This is what might happen, for instance, if we keep measuring the mass of our test mass and we get 1.1 kilograms every single time. The scale is being consistent, so we would say that the results are precise, but we also know at the same time that they're inaccurate. Right? Same idea here, except we're pretty close to the true answer. So we have really good precision and moderate accuracy. And then, of course, the dream is to have great accuracy and great precision. This is where every time I place my mass on the scale, it reads exactly 1 kilogram. In a perfect world, this is how our experimental results would come out every time. But of course, that's not the world we're living in. So we need to know how to deal with precision and accuracy, which means knowing how to deal with them mathematically when you're processing the results of an experiment, and also how to diagnose in an experimental procedure where do these kinds of problems come from. So let's talk about how you deal with the data, just in general terms. This is the classic example of we've got a lot of data points that are looking pretty good. I've taken the same measurement 4 times, and 2 or 3 of those measurements are both accurate and precise. They're clustered and they're near the value that we're actually expecting. But then I've got one which is way off. It's not consistent with the other results, and it's also not accurate. So we can see it deviates quite a lot from the other cluster of measurements that we've taken. And in this case, it's visually quite obvious that this dart down at the bottom is an anomaly. It doesn't fit in with the pattern that we've seen pretty clearly in taking other measurements. Now, the trick in physics is having some kind of mathematical technique for deciding when something is an anomaly, which we will discuss, not in this video, but essentially what you're going to need to do is what's called finding an error bar. And that tells you what's a reasonable range of spread for a data point when you're taking multiple measurements. And if a measurement falls outside of the error bars, it's fair to say that it's probably anomalous, and then you can disregard it. But just to give you a general idea, these are the kinds of situations we want to be able to diagnose. When is a result unreliable because it's so inconsistent with every other measurement that you've taken? So let's just finish up briefly by talking about, in the real world, where do these kinds of errors come from, and how do we design experiments to minimize their effects? First of all, let's talk about the example of low precision, meaning you have a big spread all over the dartboard. We sometimes call these types of errors random errors. They happen when things are just fluctuating or slightly inconsistent, and that are typically beyond your control, or can be very difficult to control because of the types of measurements you're taking. Like you can imagine, for instance, trying to measure the timing of something with a timer. There's a limitation there, which is that you as a human have to actually press a button on a timer. And sometimes you're probably going to press it a little bit too early, and sometimes you're going to press it a little bit too late. So it's going to create some level of inconsistency in the data, but it's not always going to be too fast or too slow. How do you deal with that? The most important thing you do is you take multiple measurements at the same data point. The more measurements you take, the more times you repeat the trials, the more you can average out these random errors, and your lack of precision won't be quite as problematic. And the other way we deal with that in terms of data is what's called an error bar, which is where you represent the range of data on your graph. And as I mentioned, we'll talk later about how you create error bars. The second place that errors can come from is what we call a systemic error, meaning there's some kind of problem with your experimental design that's creating a problem, but that problem is consistent. That's like where we have very precise results, but they're not accurate. Like I've got a cluster of darts up at the top of the dartboard rather than in the middle of the bullseye. These are often caused by calibration. For instance, if I have a scale that works very well, but the 0 point is not correct. Like the scale thinks that there's 0.1 kilograms on it, even when there's nothing on it. So when I put a weight on top of that scale, it's going to read the wrong number, but it's going to be consistently wrong. It's going to add an extra 0.1 to every single measurement. So ways we can deal with that, obviously, are trying to make sure all of your instruments are well calibrated. And then you can also design your data collection to help as well. If you have a consistent spread of values for your independent variable in an experiment, for instance, if I'm measuring time, for instance, I would measure 10 seconds, then 15 seconds, then 20 seconds, then 25 seconds, then 30 seconds. But if you have a consistent spacing of values that you're measuring, and if you have a wide range of values that you're measuring, it will make it clear if you have a systemic error, and especially if you have a systemic error that's only affecting certain parts of your data. Sometimes it will be the case that you get problems when you're measuring really small numbers or really big numbers, and you get deviations from a pattern that you might not otherwise see. And then there's some advanced data techniques like linearization that we will look at for really digging into the quality of your data. And the final place that errors and uncertainty come from are the measuring devices themselves. If you measure using a scale that only shows you 0.1 grams, for instance, then you can't get any information that's more specific than that, so there's uncertainty there. And that's quite easy to take account of. We just add error bars to our data that are reflecting the uncertainty in our instruments. If I can only measure 0.1 grams, then all of my measurements of mass are going to be plus or minus 0.05 grams, half of the smallest increment that my measuring device can measure.